G'day guys, welcome to Complex Numbers 2, the Squeakle. Hopefully I can do this in one take. I've got about 4 pages of notes and some diagrams pre-drawn. So without further ado, let's get into complex numbers. So from the previous video, we know that complex numbers, usually in the form of z, we know have a real part A and an imaginary part B. So A plus BI. Now what that looks like is it looks like this. So we've got the imaginary part and our real part, and it's just like the Cartesian plane. We were thinking these numbers as vectors. So they've got a height B in the imaginary plane, or in the imaginary direction, and they've got kind of a distance A in the reals. So what we're going to be looking at today is polar form. Polar form. So this A we can write as R cosine theta, and this B we can write as R sine theta. So we've actually got this kind of trigonometric relationship happening. So in polar form, instead of writing z is A plus BI, in polar form we can write it as R cosine theta plus R sine theta times I, because that's our A part and that's our B part. And we can factor the R out, so it's R then cosine theta plus, and we write I sine theta. It's just kind of what we do, and that's why you might have seen something in this form, R cis theta, because that's standing for cosine theta plus I sine theta. So that's where that's coming from. So that's just the shorthand of this. So that's it basically for how you write a complex number in polar form. Now R is given to us by the length of that vector, or the magnitude, or from the previous video, the modulus of z, which is a squared plus b squared all square rooted. And we know that tan theta is equal to b over a. So these two things are quite important if we were to write numbers in polar form, complex numbers in polar form. So why don't you pause the video and write this: z equals 1 plus I in polar form. My other example I want you to have a go at is writing W equals square root of 3 minus I in polar form. So you could pause and give those a go. Okay, well, R is the modulus of z, which is 1 squared plus 1 squared all square rooted, so root 2. And tan theta is b over a, or 1. And so theta is pi on 4. So z is actually going to be equal to square root of 2. So we're writing it in this form. Maybe I'll just make that a bit obvious. We're writing in that form there. Root 2 cosine pi on 4 plus I sine pi on 4. And so there we have it. We've written z in polar form. Let's look at W. It's just slightly trickier. R is the modulus of W, or the absolute value, which would be root 3 squared plus 1 squared all square rooted, which is 2. And tan theta is going to be -1 on root 3. And I might just leave this to you to solve, but theta needs to be -pi on 6. So W is 2 cosine -pi on 6 plus I sine -pi on 6. You could technically have 11 pi on 6. That would just be going in the full rotation anti-clockwise, or you can go in the negative direction as well. Right, so what do they look like? Well, they both look like this. So in standard form, like the form that we did in the last video, 1 plus I would be 1 and I up here. So that makes sense that we've got a pi on 4 angle with a length of root 2. W being root 3 across and -1I down gives this -pi on 6. But you can kind of see how you could have 11 pi on 12 being almost, that full rotation. Sorry, not saying from there, saying from that real axis. So that's what they look like. So why is this useful? Okay. Polar form helps a lot with multiplication and division. It gives a bit more of a geometric understanding of what's happening. So let's have a look at a generalized problem. So let's let Z1 equal R1 cosine theta 1 plus I sine theta 1, and Z2 be very similar, R sub 2 cosine theta 2 plus I sine theta 2. And let's look at what happens when we multiply those. So Z1, Z2, what's that going to be equal to? Well, R1 times R2, and then we just got these brackets multiplied by each other. So cosine theta 1 plus I sine theta 1 cosine theta 2 plus I sine theta 2. So we're going to get R1, R2, and I'm going to open up some square brackets here because there's a lot going in. We will have cosine theta 1 cosine theta 2, I'm just doing the real part here, minus sine theta 1 sine theta 2, plus I times sine theta 1 cosine theta 2 plus cosine theta 1 sine theta 2, all in square brackets, because that whole thing has been multiplied by R1, R2. Hopefully you immediately thought of some trig identities, and you can see that this here is just the same as, I'll put this all in square brackets again, that's just cosine theta 1 plus theta 2 minus I, and you can see here that that's just the identity for sine theta 1 plus theta 2. Okay. So what does that mean? Well, it means that we just had to multiply the modulus and add those angles. Now, the angles are actually called arguments. So let's write that down. So multiplication of complex numbers states that we multiply moduli, the plural of modulus, and add the arguments. So a rough sketch, this angle for a complex number z, we call that the argument. Cool. So what does that mean geometrically on the complex plane when we're multiplying complex numbers? So I've drawn this little diagram up. So here's our argument for z1. So z1's here. It's got some length and some argument. z2 also, because it has to go from the reals counterclockwise. So the argument for z2 is this entire angle here, and it's got a slightly longer modulus. And so when we multiply them both together, we add the arguments, so we add these angles on. So this green angle would get added in here. So that's going to be theta 1. And so the arguments added together become this entire angle here, and then obviously the modulus multiplies, so this should get longer if those numbers are more greater than 1. So that's kind of what's happening geometrically speaking. Okay. Just going to add to this that division is very similar. So if we have z1 over z2, well, that's just r1 over r2, and it's just the difference between the arguments, theta 1 minus theta 2 plus I sine theta 1 minus theta 2. So division just is kind of intuitive. If multiplication is multiply and add, division is divide and subtract. It's just like that. It's like an inverse. Okay. What we're going to do now is we'll run through an exercise. So find the product of, we'll use the ones from before, 1 plus I and root 3 minus I in polar form. So you could pause the video and actually give that a go. So we know that 1 plus I is root 2 times cosine pi and 4 plus I sine pi and 4. And root 3 minus I we know is 2 cosine negative pi and 6 plus I sine negative pi and 6. That's just from earlier in the video. So when we multiply this together, so 1 plus I multiplied by root 3 minus I, well, that's just going to be multiply the modulus to root 2, and then we're just going to be adding the argument. So I'll open up some square brackets, cosine pi and 4, and we're adding negative pi and 6. So we'll just go minus pi and 6 plus I sine pi and 4 minus pi and 6, because we're adding a negative argument. So it kind of is looking a wee bit like division there, but you might want to explore that a bit more. And so finally we have 2 root 2 in brackets cosine, we're going to get pi on 12 plus I sine pi on 12. And there we have it. We have multiplied our two complex numbers. Let's go z and w. And that's what we get in polar form. And then that's actually quite easy to graph, because you know that your horizontal, well, you know your argument's pi on 12, and you can easily find, I'll just show you. You can easily see how that multiplication has worked. So we had z was 1 plus I, so it's up here, with a modulus of root 2. And we w was root 3 minus I, and it had a modulus of 2. So we multiplied those together, we added the arguments, And so it's basically like, because this was negative pi on 6, we basically just came back negative pi on 6 from pi on 4. And so we've got an argument of pi on 12, and our modulus is increased because we've got 2 times root 2, so it's slightly longer. So that's the geometric understanding of how that multiplication has worked. Hopefully that's made sense. Okay. What happens when we repeat the process? So what we're going to look at here is, so z is just r cosine theta plus I sine theta, so that's r cis theta in shorthand. So what's z squared? Well, z squared would be just multiply your modulus and add your arguments. So instead of theta, we can have 2 theta, because it's going to add those. And what would z cubed look like? Well, that would just be z times z squared. So r cubed cosine 3 theta plus I sine 3 theta, and so on and so forth. Now, so this is de Moivre's theorem. Basically, if z is equal to r cosine theta plus I sine theta, and n is a positive integer in this next step, then z raised to any positive integer would just be r bracket cosine theta plus I sine theta, all raised to the power of n. And that would just be r to the n, and then we would just have n lots of the argument, because we'll be adding them n times. So it'll be n theta plus I sine n theta. Or, in that shorthand notation, Rn cis n theta. So that's cosine n theta plus I sine n theta. That's what the CIS stands for. So, why don't you give this a go? Find a half plus a half I raised to the power of 10. Why don't you give that a go and see what you get? Alright, so how are we going to go about doing this? Well, we know that 1 over 2 plus 1 over 2i is going to be equal to root 2 over 2 for its modulus, cosine pi on 4 plus I sine pi on 4. So we need to get this into polar form, and then all we need to do now is raise the modulus to the power of 10. So that's going to be 2 to the 5 over 2 to the 10, and we're just going to be adding up pi on 4 10 times, or cosine 10 pi on 4 plus I sine 10 pi on 4. Well, that's just 1 on 32. And you can see here we've actually got 2.5 rotations, because 4 goes into 10 2.5 times. So that's going to be like going around once, twice, and and then another quarter turn, isn't it? Right. So 1 over 32i should be the answer. Might just go through that last part again. So this here is 1 on 32 times cosine 5 pi on 2 plus I sine 5 pi on 2. Well, 2 pi on 2 would be one rotation, or like half a rotation would be pi. Then another pi on 2, that's 4 pi on 2, would take us back to here. And then we've got another pi on 2, which would be this half turn taking you there. So that's why there's only a complex part, because in here is a 1 1/4 turn. So it's just on the vertical part of the complex numbers, there's no real part. So that's what a half plus a half I raised to the power of 10 would give you. So convert to polar and then use Tomaev's theorem. Raise the modulus to the power of 10 and just 10 times your argument. Simplify the fraction, and then you can kind of want to interpret that a little bit with your geometric intuition.